what you're witnessing is an impossibility. A celestial island, a pinwheel of ancient light adrift in the unfathomable blackness of intergalactic space. Here hundreds of billions of suns are caught in a slow, majestic gravitational waltz, a dance that has unfolded over eons. It is a spectacle of such serene beauty, such perfect cosmic order, that it feels eternal, unshakable. But this tranquility is a profound illusion. Every law of physics we hold dear, the elegant equations pioneered by Newton and refined by Einstein, screams that this magnificent structure, the galaxy, should not exist. It is a metropolis built on foundations of sand, a spinning top, rotating with such ferocious velocity that it ought to fly apart, its stellar citizens flung violently into the void. We are looking at a cosmic crime scene where the evidence of a cataclysm is everywhere, yet the catastrophe itself has somehow been averted. The mystery is not that galaxies die. The mystery is that they are alive at all. To understand this paradox, you must first feel the speed. Imagine standing on the far edge of this galactic disk. You are hurtling through space at nearly 1,000,000 miles per hour. Not the galaxy as a whole moving through the universe, but you in your orbit whipping around its distant core. Now think of a child's merry-go-round. The children clinging to the outer edge have to hold on tightest, feeling the strongest pull to be thrown off. Those nearer the centre feel a much gentler force. This is intuition, but it is also fundamental physics. The farther an object is from the centre of rotation, the slower it must travel to maintain a stable orbit. This principle governs everything in our own solar system. Mercury nearest the Sun zips round in just 88 days. Distant Neptune, feeling only a faint whisper of the Sun's gravity, takes a staggering 165 years to complete a single journey. Its orbital velocity is a mere fraction of Mercury's. This is the expected predictable harmony of the cosmos, a gravitational signature that has been confirmed countless times. It is the law. So when we turned our most powerful telescopes toward our galactic neighbours like the Great Andromeda Spiral, we expected to see this same elegant, predictable pattern. We set out to map the galaxy's rotation to chart the speeds of its stars. Our hypothesis was simple, and we thought irrefutable. The stars in the dense, bright central bulge would be moving fastest, while the lonely suns, populating the faint gossamer arms at the periphery, would be moving far more slowly, their orbits decaying gracefully with distance, just like the planets in our solar system. To conduct this survey, astronomers performed a cosmic census. They painstakingly counted the stars, measured the vast clouds of glowing gas and the dark lanes of interstellar dust. They added up everything they could see, everything that shone or cast a shadow, to calculate the galaxy's total mass. From this total, they could then map out the gravitational field, the invisible web of influence that should be dictating the speed of every star at every distance from the core. The prediction was clear, the math was certain, and the universe, it turned out, had other plans. In the 1970s, astronomers Vera Rubin and Kent Ford embarked on this very project. They weren't seeking to overturn physics. They were simply trying to refine our understanding of galactic dynamics. Using a highly sensitive spectrograph, they could analyze the light from different regions of a galaxy. By measuring the subtle shift in that light, a shift towards red, if a star was moving away, a shift towards blue if it was moving closer, they could calculate its velocity with unprecedented precision. They were in essence operating a cosmic radar gun aimed at targets trillions of miles away. They began with Andromeda, our closest major galactic neighbour. They measured the bright star-choked core. The speeds were as expected incredibly high. Then they moved their instruments outward into the dimmer, more sparsely populated regions, mile by painstaking cosmic mile. They anticipated the moment when the velocity measurements would begin to plummet the graph on their monitors, showing the classic elegant drop-off that Kepler and Newton had foretold. They waited, and they waited, but the drop never came. To their astonishment, the data streaming back was nonsensical. The stars on the galaxy's outermost edge were moving just as fast as the stars near the core. The rotation curve, the graph plotting speed against distance, didn't fall. It went flat. It was as if the children on the very edge of that cosmic merry-go-round were spinning at the same dizzying speed as those at the centre. According to the laws of gravity, this was impossible. There was simply not enough visible matter, not enough gravitational pull from the stars and gas we could see, to anchor these speeding suns in their orbits. They should have been sailing off into the intergalactic darkness. Rubin and Ford were meticulous scientists. Their first assumption was error. Their equipment, their calculations, their methodology, something had to be wrong. So they checked everything. They recalibrated. They ran the observations again. The flat curve remained an immovable, inexplicable fact. Perhaps Andromeda was a fluke, a cosmic oddity. So they pointed their telescope to another spiral galaxy, and another, and another. Each time the result was the same. From galaxy NGC 27422 to NGC 75541, a bizarre and ghostly pattern emerged across the cosmos. Every single spiral galaxy they observed was spinning too fast for its own good, held together by a force that defied all explanation. It was a quiet crisis, a discovery that didn't make headlines but sent profound shockwaves through the foundations of astrophysics. The universe was not behaving as it should. The discrepancy wasn't small, a minor rounding error, it was colossal. The visible matter in a typical galaxy, all the suns, planets, nebulae, and cosmic dust combined, accounted for only about 15% of the gravity needed to hold it together. 85% of the universe's gravity, it seemed, was completely unaccounted for. It was as if we were trying to understand the behaviour of an iceberg by only measuring the tiny glistening tip that breaks the surface, completely unaware of the immense unseen mass lurking in the depths below. This is where our story truly begins. It is the moment where science confronts the abyss, the vast chasm between what our theories predict and what the universe actually reveals. When faced with such a fundamental contradiction, there are only two paths forward. Either our understanding of gravity, the bedrock of physics for 300 years, is profoundly wrong on galactic scales, or there is something else out there, something massive, something invisible, something that permeates the cosmos yet interacts with almost nothing, a ghost in the machine. Scientists gave this phantom substance a name born of humility and ignorance: dark matter. Dark because it emits no light, no heat, no radiation of any kind. It is utterly stubbornly invisible to every telescope we have ever built. Matter, because whatever it is, it has mass. And because it has mass, it exerts a gravitational pull. An immense gravitational pull. This wasn't just some exotic, sparsely distributed dust. The data from the spinning galaxies demanded something far more radical, a conclusion so staggering, it reshaped our entire cosmological model. The theory that emerged was as elegant as it was strange. Every galaxy, including our own Milky Way, does not drift alone in the void. Instead, each is a delicate, glittering jewel embedded within the heart of a truly colossal structure, a vast, spherical, invisible cloud of this dark matter. This structure is called a dark matter halo. You must completely reimagine the scale of a galaxy. The spiral of stars you see, that beautiful pinwheel of light, is merely the small luminous centerpiece. The true galaxy, the halo, is a ghostly sphere of influence that is 10 times wider and hundreds of times more massive. It is an unseen gravitational leviathan, a cosmic anchor holding the visible stars in its unyielding grip. We are not living in a city of stars. We are living in a small, well-lit neighbourhood located deep inside a continent of invisible, unknown substance. This halo is the missing piece of the puzzle. It is the source of the mysterious extra gravity. The immense distributed mass of the halo extends far beyond the visible edge of the galaxy, and its gravitational influence doesn't weaken as expected. It provides the powerful, consistent grip needed to keep those fast-moving outer stars locked in their orbits, explaining precisely why the rotation curves are flat. The stars on the edge aren't just orbiting the bright galactic core, they are orbiting the entire massive system, the visible disk and the invisible halo combined. The ghost was finally revealed not by sight but by its gravitational shadow. This discovery transformed everything. It meant that the starlight that has guided us, inspired us, and driven our exploration for millennia is just cosmic foam on the surface of a deep, dark ocean. All the atoms that make up the stars, the planets, the nebulae, and even us, the normal matter of the universe, are a mere cosmic afterthought. For every 1 pound of matter, you can see the universe hides 5 pounds of this enigmatic invisible substance. we are the anomaly. The darkness is the norm. The existence of these halos poses some of the most profound questions in all of science. What is this stuff? Is it a new type of subatomic particle, something not predicted by our standard model of particle physics that slips through the world of normal matter like a phantom? Where did it come from, forged in the Big Bang alongside the atoms we know, but governed by a completely different set of rules? And perhaps most importantly, how did these invisible structures shape the universe we see today? Because these halos are not just passive cages holding galaxies together, they are the architects of the cosmos. Their immense gravity acted as the original seeds, the gravitational wells into which the first wisps of hydrogen and helium gas fell after the Big Bang, providing the scaffolding upon which all galaxies were built. Without these halos, the universe today might be a thin, featureless soup of gas with no galaxies, no stars, no planets, and no one to ask these questions. Our journey into the dark is just beginning. We must now travel back in time to the dawn of creation to witness how these ghostly halos first formed in the embers of the Big Bang. We will see how they grew from tiny fluctuations in the primordial universe into the colossal cosmic webs that now connect all galaxies. We will explore the cosmic battle between dark matter's relentless gravity and dark energy's mysterious push, a struggle that will determine the ultimate fate of the universe. We are setting out to map an invisible empire to understand the glue that binds the cosmos, and in doing so to truly understand our own place within this vast, dark and magnificent reality. What if the greatest cosmic story ever told is the one happening in the dark, not in the silent vacuum between worlds, but in a deeper, more profound invisibility that pervades everything? We have spent centuries charting the heavens, counting the stars, and mapping the grand architecture of the cosmos, believing that what we saw was what we got. But this breathtaking celestial tapestry, the sum of all starlight and glowing nebulae, is a profound illusion. It is merely the shimmering froth on a vast unseen ocean, a cosmic ocean whose gravitational tides command the allegiance of every galaxy, every star, and perhaps even the ultimate destiny of the universe itself. To understand this, we must become detectives following a trail of gravitational breadcrumbs left by a phantom culprit, a trail that begins not with a grand discovery, but with a barely heard whisper of doubt from a lone defiant voice. Our story begins in the 1930s, an era when our cosmic perspective was still in its infancy. The great debate over whether spiral nebulae were gas clouds in our own Milky Way, or entire island universes in their own right, had only recently been settled. Astronomers felt they were finally grasping the universe's true scale, a majestic but fundamentally straightforward realm, governed by the elegant laws of gravity Newton had laid down centuries before. In this confident scientific landscape, the Swiss-American astronomer Fritz Zwicky was a uniquely abrasive and brilliant figure, a man whose mind worked on a different plane from his contemporaries. While studying at Caltech's Mount Wilson Observatory, he turned his attention to a distant, colossal object, the Coma Cluster, a sprawling metropolis of over 1,000 galaxies bound together by their mutual gravity, located some 320 million light-years away. To Zwicky, this cluster was a perfect laboratory. It was a self-contained system where he could test the laws of physics on the grandest possible scale. His method was in principle quite simple, yet audacious in its scope. He began to painstakingly measure the movement of individual galaxies within the bustling heart of the cluster. Using the observatory's powerful telescopes, he captured the faint light from these distant island universes. That light held a secret. Embedded within its spectrum were dark lines, the unique chemical fingerprints of the elements inside their stars. But these fingerprints weren't where they were supposed to be. For galaxies hurtling away from us, their light waves are stretched, shifting these lines towards the red end of the spectrum in a phenomenon known as redshift. For those moving towards us, the light is compressed, creating a blue shift. Zwicky realized he could use this Doppler effect, the same principle that changes the pitch of a passing siren, to clock the speeds of these titanic objects as they swarmed and orbited within the cluster's gravitational grip. He spent countless hours at the telescope collecting data on galaxy after galaxy, measuring their velocities relative to the cluster's center of mass. He discovered a scene of incredible violence. These galaxies were not drifting placidly. They were careening through space at tremendous speed, some exceeding 1,000 kilometers per second. They were moving like cosmic cannonballs. Now came the crucial second step. Zwicky knew that for the Coma cluster to exist at all, for it not to have flown apart billions of years ago, there had to be enough gravitational force to act as a cosmic shepherd, corralling this frenetic flock. The amount of gravity required is directly proportional to the total mass of the system. By calculating the velocities of the galaxies, he could therefore deduce the minimum mass the cluster must contain to keep its members from escaping into the intergalactic void. He was using their motion as a celestial scale weighing the entire cluster by observing how fast its constituent parts were moving. This is what we call the dynamical mass. But Zwicky had another more direct way to estimate the cluster's mass. He could simply add up all the light. By measuring the total brightness of the 1,000+ galaxies and making a reasonable assumption about the mass of an average star, he could calculate how much matter was actually visible. This was the luminous mass, the sum total of all the stars and glowing gas he could see through his telescope. He now had two independent estimates for the mass of the Coma cluster, one derived from the light it emitted and another derived from the gravity it exerted. In a universe that made sense, these two numbers should have been at the very least in the same ballpark. They were not. What Zwicky found was so outrageous, so utterly contrary to the established wisdom of the day, that it should have triggered a revolution in cosmology right then and there. The dynamical mass, the mass required by gravity to hold the cluster together, was more than 400 times greater than the luminous mass he could account for from all the visible galaxies. It was a result of jaw-dropping impossibility. It was like observing a tiny pebble with the gravitational pull of a mountain. The vast majority of the cluster's substance, the very stuff that was preventing it from disintegrating, was completely, utterly invisible. The galaxies he could see were just glowing specks adrift in an ocean of something else, something unseen and profoundly massive. In his notebook, Zwicky scribbled the term dunkel materie, dark matter. He proposed that the universe was filled with this transparent substance, a phantom component that did not shine, reflect or interact with light in any way, but which exerted an overwhelming gravitational dominance. It was a bold, almost fantastical claim, and the scientific community was not ready to listen. Zwicky's combative personality did him no favours. He famously referred to his colleagues as spherical bastards, because he claimed they were bastards no matter which way you looked at them. His contemporaries dismissed his findings, attributing the discrepancy to observational errors or a misunderstanding of galactic dynamics. For nearly 40 years, Zwicky's dark matter was treated as little more than a peculiar footnote, an anomaly from a distant cluster, while the rest of cosmology moved on to explore the newfound wonders of the Big Bang quasars and the life cycles of stars. The ghost in the machine had been spotted, but almost no one believed the sighting. The mystery lay dormant, a puzzle tucked away on a dusty shelf of astronomical history. The universe we continued to believe was a luminous place. Its secrets were written in light, and its mechanics were driven by the matter we could see. Then in the 1970s, 4 decades after Zwicky's lonely pronouncement, the ghost returned. This time it wouldn't appear in the chaotic swarm of a distant galaxy cluster, but in the graceful pinwheeling arms of our own cosmic neighbours. And the person who would force the world to finally confront it was not a combative iconoclast, but a quiet, tenacious and meticulous astronomer named Vera Rubin. From a young age, Rubin had been captivated by the motions of the heavens, yet she pursued her passion against a constant headwind of institutional sexism. She was denied entry to graduate programs that did not accept women, and often found herself the sole female astronomer at observatories and conferences. But her persistence was unwavering. She was not interested in flashy theories. She was a pure observer, someone who believed that the universe would reveal its truths if you simply had the patience and the precision to ask the right questions. Working alongside her collaborator, the instrument maker, Kent Ford Rubin, decided to investigate a problem that had long intrigued her, the rotation of spiral galaxies. She wanted to create the most detailed maps ever assembled of how these immense structures spin. Her target was the magnificent Andromeda Galaxy, our closest spiral sibling. It was a perfect specimen, a grand, sprawling disk of hundreds of billions of stars tilted at just the right angle for a comprehensive study. The prevailing logic, rooted in centuries of physics from Newton to Kepler, made a clear and simple prediction about how Andromeda should spin. Just like our own solar system, where the vast majority of the mass is concentrated in the Sun at the centre, a spiral galaxy's visible mass is overwhelmingly concentrated in its central bulge. Stars' gas and dust become progressively sparser the farther out you go. Therefore, the stars in the outer regions of the galactic disk, far from the central gravitational anchor, should be moving much more slowly than the stars orbiting closer to the core. Mercury orbits the Sun at a blistering 48 kilometers per second, while distant Neptune plods along at a leisurely 5.4. This predictable drop-off in orbital speed with distance is a fundamental consequence of gravity. Rubin and Ford expected to see exactly this Keplerian decline in the stars of Andromeda. To measure this, they employed a brilliant piece of technology Ford had perfected, an advanced image tube spectrograph. It was an instrument of exquisite sensitivity capable of capturing the faint light from the galaxy's distant edges with unprecedented clarity. Their technique was a masterclass in observational astronomy. They would align the spectrograph's long, narrow slit directly across the diameter of the galaxy's image. This allowed them to capture a continuous spectrum of light not just from the centre, but from all points extending out to the faintest, most remote tendrils of the spiral arms. As the galaxy spun, one side of its disk would be rotating towards Earth, causing its light to be blue-shifted, while the other side rotated away, causing a redshift. The amount of this shift directly corresponded to the rotational velocity of the stars and glowing hydrogen gas clouds at that specific location. By measuring the wiggle in the spectral lines along the length of the slit, they could plot a graph, a rotation curve showing orbital speed versus distance from the galactic centre. The first nights of observation were painstaking. They had to guide the telescope with perfect precision, keeping the spectrograph's slit locked onto the galaxy for hours at a time to collect enough photons from those ethereal outer arms. As the data began to accumulate, plate by photographic plate, a picture began to emerge. It was a picture that made no sense. The stars near the centre of Andromeda were indeed moving rapidly, just as expected. But as they plotted the velocities of stars farther and farther out, the expected decline never came. The curve on their graph refused to drop. Instead of slowing down, the stars in the outer precincts of the galaxy were maintaining the same incredible speed as the stars much farther in. The rotation curve was flat. It was a shocking, visceral violation of Newtonian physics. Those distant, lonely stars were orbiting so fast that the gravity from all the visible matter in the galaxy, all the stars, dust and gas combined, could not possibly hold on to them. They should have been flung out into the intergalactic darkness ages ago, like stones from a slingshot that has been spun too fast. The galaxy should have torn itself apart. At first they thought it must be a mistake. Perhaps Andromeda was simply an anomaly, a cosmic freak. So they turned their instrument to other spiral galaxies. They observed dozens more big and small near and far, and in every single one they found the same inexplicable behaviour. Every galaxy they measured had a flat rotation curve. Every galaxy was spinning with a reckless, impossible velocity that defied the laws of gravity as they knew them. The evidence became an avalanche. This wasn't a fluke. It was a universal rule. Rubin's meticulous, undeniable data transformed Zwicky's missing mass problem from a niche curiosity into a full-blown crisis for physics. The implication was as profound as it was inescapable. Just as Zwicky had found in the Coma Cluster, individual galaxies themselves must be embedded in a colossal invisible structure. There had to be an enormous halo of unseen matter, a gravitational scaffold extending far, far beyond the visible edge of the spiral arms. This dark matter halo wasn't just a minor correction. It had to contain the vast majority of the galaxy's mass. The brilliant spinning disk of stars we call a galaxy was nothing more than a luminous decoration, a glittering afterthought suspended within a far larger and more substantial sphere of pure transparent gravity. This invisible substance was the true galaxy. Its immense gravitational field was what was gripping those outer stars, whipping them around at their astonishing speeds and keeping the entire structure from disintegrating. The work of Zwicky and Rubin, separated by 4 decades, and focused on vastly different cosmic scales had converged on a single revolutionary truth. The pioneers working in different eras and with different tools had independently discovered the same cosmic phantom. The universe that we see the realm of starlight and sunshine is a cosmic minority. It is outweighed, outmassed, and gravitationally dominated by a factor of at least 5 to 1 by something else entirely. We live in a universe built by an invisible architect held together by an invisible glue. The critical question, the one that would ignite a decades-long search and define the next era of cosmology, was no longer if. This dark matter existed, but the far more daunting puzzle, what, in God's name, is it? This invisible architecture was a wild, almost heretical idea. For decades we had been haunted by a ghost in the machine, a phantom limb whose gravitational pull we could feel, but whose substance remained entirely beyond our grasp. Astronomers had measured the impossible speed of outlying stars, a clear violation of the gravitational laws we held sacred, and were forced to confront a universe far stranger than imagined. The calculations were undeniable, pointing to a vast reservoir of missing mass, a hidden substance that outweighed everything we could see by a staggering factor of 5 to 1. But to propose that this missing mass wasn't just sprinkled randomly throughout the cosmos, but was instead organised into a coherent colossal structure, that was a profound leap. The theory that emerged was as elegant as it was audacious. Every galaxy, including our own Milky Way, was thought to be nothing more than a luminous jewel set within a gargantuan invisible sphere of this mysterious dark matter. This structure, this dark matter halo, would be the true galaxy, its gravitational bedrock, its unseen guiding hand. The spiral arms, the glowing nebulae, the billions of stars, all of it, would be just the visible froth on a deep dark ocean. This was a direct confrontation with our most basic perceptions. It suggested that when you look at the Andromeda Galaxy, you're not seeing the whole picture. You're seeing only the brightly lit stage, while the true theatre, a colossal spherical arena 10 times wider and 100 times more massive, remains shrouded in absolute darkness, an ethereal presence extending for hundreds of thousands of light years in every direction. This halo would be the gravitational cradle in which our galaxy was born, the cosmic scaffolding that dictates its shape, its spin, and its ultimate destiny. Without this invisible anchor, the model showed galaxies would fly apart. They would have torn themselves to shreds billions of years ago, their stars flung into the intergalactic void like scattered dust. The beautiful orderly spirals we see across the universe simply should not exist in a cosmos made only of what we can see. The theory was compelling, it was mathematically sound, but it remained a ghost story told with equations. How could you possibly prove the existence of a structure that emits no light, reflects no light, and blocks no light? How do you photograph a ghost? The answer, it turned out, was not to look for the ghost itself, but to watch for the way it warps the very fabric of reality around it. The key was a prediction made by Albert Einstein decades earlier, a consequence of his theory of general relativity so bizarre that even he thought it would be impossible to ever observe. He had shown us that mass tells spacetime how to curve and that curved spacetime tells matter how to move. Gravity in this new vision was not a force but a landscape of invisible hills and valleys. And like any landscape, it could alter the path of whatever passes through it, even a beam of light. Imagine light from a distant galaxy travelling across billions of years, a pure straight line through the cosmic emptiness. If that light were to pass by a massive object like another galaxy, the immense gravity of that object would bend space-time itself, creating a gravitational valley. The beam of light following this new contour would be deflected, its path bent as if it had passed through a giant lens. This phenomenon, known as gravitational lensing, was Einstein's cosmic magic trick, and it would become our ultimate tool for mapping the invisible. For astronomers, this meant the universe had provided its own telescopes. Any concentration of mass, visible or not, would act as a lens. By observing the light from galaxies in the far, far distance, we could search for the subtle distortions caused by objects in the foreground. If the dark matter halo theory was correct, then the gravitational influence of a galaxy should extend far beyond its visible edge. The lensing effect, the warping of spacetime, should be detectable not just near the bright galactic core, but deep into the supposedly empty space where the halo was presumed to reside. It was a painstaking, monumental task. It required observing thousands of distant galaxies, their images nothing more than faint smudges on deep sky photographs, and measuring their shapes with incredible precision. You're looking for a systematic, coherent distortion, a subtle stretching of these distant galaxy images into tiny arcs, all aligned around a foreground galaxy that acts as the lens. When the results started to come in, they were breathtaking. The evidence was everywhere. Just as the theory predicted, the light from background galaxies was being warped by a gravitational field far larger, far more extended than could be explained by the stars and gas we could see. Astronomers could use the degree of that distortion to work backwards to calculate the amount of mass required to create such a powerful lens, and crucially to map its distribution. They were in effect drawing the outlines of the invisible. And what emerged from these cosmic surveys was a new map of the universe, one filled with vast spherical presences. The halos were real. Their gravitational signatures were etched into the light of distant quasars, their immense scale revealed by the warped visages of ancient galaxies. This was powerful, persuasive evidence. It moved the dark matter halo from the realm of theoretical necessity to observational reality. We could now see its gravitational shadow. But a shadow is not the thing itself. A lingering, profound skepticism remained in parts of the scientific community. Could this effect be an illusion? Perhaps our understanding of gravity itself was incomplete. Maybe on galactic scales, gravity simply behaves differently, stronger over long distances than Einstein's equations suggest. These modified gravity theories propose that the extra gravity we attributed to dark matter was just a property of ordinary matter itself. There was no ghost. We were just misinterpreting the laws of physics. It was a legitimate scientific challenge, a competing hypothesis that couldn't be easily dismissed. How could you possibly separate the gravity from the matter to prove they were two different things? To do that, you would need a cosmic event so violent, so cataclysmic, that it could literally knock the matter out of its own gravitational field. You would need to find a place where the ghost had been torn away from its machine, and in 2006 astronomers found it. It's called the Bullet Cluster, and it is without exaggeration one of the most important images ever taken in the history of science. What you're looking at is not a single object, but the site of a celestial train wreck of unimaginable proportions. This is the aftermath of a collision, a cosmic smash-up between two entire clusters of galaxies, each containing hundreds of galaxies like our own. The event took place over the course of 100 million years as these two colossal clusters, drawn together by their mutual gravity, finally met and passed through one another at a speed of nearly 10 million miles per hour. It is for us a time machine. We are witnessing the grandest autopsy in cosmic history, a scene that allows us to dissect the components of the universe and see, once and for all, how they interact. Let's break down what we're seeing piece by piece. First, there are the galaxies themselves. In the visible light image, you can see them as small yellowish-white points. Because galaxies are mostly empty space during the collision, the individual galaxies within each cluster mostly flew past each other, like two swarms of bees merging their stars, missing each other completely. So the galaxies, the stellar matter, have passed through the collision, and are now on either side of the wreckage. But the stars make up only a tiny fraction of a cluster's ordinary matter. The vast majority of it, over 90%, is not in stars, but in a gigantic diffuse cloud of superheated gas, a plasma so hot it glows brilliantly in the X-ray spectrum. This is the primordial hydrogen and helium left over from the Big Bang. So astronomers pointed their X-ray telescopes like the Chandra Observatory at the collision site, and they saw something spectacular. The gas from the two clusters had not passed through each other cleanly. Unlike the stars, these enormous gas clouds behaved like physical fluids. They slammed into one another with immense force, creating a titanic shockwave, a cosmic bow wave visible in the images as two vast glowing pink clouds of X-ray emission. This is the baryonic matter, the ordinary stuff of atoms and elements caught in the middle of the collision, slowed down by its own pressure and drag like two tidal waves crashing together and stopping in a furious froth. So far, so good. This is what you would expect. The galaxies have passed through, the gas has been left behind. Now comes the crucial question. Where is the gravity? If the modified gravity theories were correct, if gravity is simply an emergent property of ordinary matter, then the centre of mass, The gravitational heart of the system should be right there with the pink glowing gas, where almost all the ordinary matter resides. The gravitational lensing map should show two massive peaks of gravity located squarely in the centre of the X-ray clouds. But if the dark matter halo theory is correct, something entirely different should have happened. Dark matter, whatever it is thought to interact with other matter only through gravity. It doesn't feel friction. It doesn't feel pressure. It is a swarm of collisionless particles. Therefore, during the collision, the enormous dark matter halos of the two clusters should have passed right through each other and through the gas completely undisturbed, like ghosts passing through a wall. The halos, and therefore the centres of gravity, should have stayed with the fast-moving galaxies now far from the central wreckage. Using the Hubble Space Telescope and other ground-based observatories, astronomers meticulously mapped the gravitational lensing across the entire field. They charted the subtle distortions of tens of thousands of distant galaxies lying far behind the bullet cluster. From this data, they constructed a map of the mass distribution, a picture of the gravitational landscape of the collision. This mass map is typically coloured blue in the composite images, and when they overlaid this blue map of gravity with the pink X-ray map of ordinary matter and the optical image of the galaxies, the result was a revelation. An incontrovertible paradigm-shifting moment. The blue, the gravity was not in the middle. It was not where the vast majority of the ordinary matter, the pink gas, was. Instead, the map revealed two distinct massive concentrations of gravity, located on the outer edges of the collision, perfectly aligned with the swarms of galaxies that had passed through. The matter and its gravity had been physically separated. There in one stunning image was the smoking gun. The gravitational core of the clusters, the dark matter halos, had sailed through the collision unscathed, their immense gravity dragging the galaxies along with them. The ordinary matter, the hot gas, had been left stranded in the middle, a disembodied cloud stripped of its gravitational anchor. Here was direct visual proof. Gravity was not tethered to the atoms we know and understand. There was something else there, something dark, massive, and collisionless. The bullet cluster was a death blow to many alternative theories of gravity. No simple modification of Einstein's laws could account for this stark separation of mass from gravity. You couldn't just tweak gravity to be stronger. You needed a new substance, a new ingredient in the cosmic recipe, one that behaved exactly as dark matter was predicted to behave. It confirmed with breathtaking clarity that dark matter is not just a fudge factor in an equation. It is a real physical constituent of our universe, and it exists in the form of these vast, diffuse, ghostly halos, the invisible skeletons upon which the visible universe is built. And for you, for us, this is a profound realization. It means the gravitational well that holds our solar system in its orbit around the Milky Way is not generated primarily by the stars you see, but by a transparent sphere of unknown particles we are flying through at this very moment. It means the seeds of all structure in the cosmos, the gravitational pits into which matter first began to fall after the Big Bang, were laid down not by atoms, but by this invisible medium. Without these dark halos to act as cosmic nurseries concentrating matter and providing a stable gravitational foundation, the universe today might be a thin uniform soup of gas with no galaxies, no stars, no planets, and no us. We owe our very existence to a form of matter we cannot see, cannot touch, and cannot yet comprehend. We have seen its shadow, we have mapped its gravitational footprint, we have even witnessed it being torn apart from its visible counterpart in the wreckage of a cosmic collision. The evidence for these vast invisible structures is now overwhelming. Their existence is no longer a matter of serious debate. The ghost in the machine has been found. But in solving one great mystery, we have uncovered an even deeper one. Knowing that the halos are there is one thing, but a fundamental burning question now hangs over all of cosmology, demanding an answer with an urgency that drives thousands of scientists in laboratories and observatories around the world. We have found the Dark Kingdom. Now we must ask, what are its citizens? What exactly is the particle that constitutes this cosmic ghost? And so, the evidence mounted an undeniable weight of observation, pressing down on our neat and tidy picture of the cosmos. Galaxies spinning with impossible speed, light bending around unseen masses, a universe seemingly held together by ghosts. For decades, this invisible component, this dark matter, was treated as a cosmic anomaly, an inconvenient extra ingredient required to make our equations balance. It was the unsettling footnote in the grand story of creation. But what if we'd been looking at the story entirely backwards? What if this enigma wasn't some strange addition to the universe, but the very reason for its structure, for its beauty for us? What if the ghost in the machine was in fact the machine itself? To understand this staggering shift in perspective, we must travel back. Back before the first star ignited, before the first galaxy coalesced to an epoch of primordial simplicity, a time of near-perfect uniformity. We have a baby picture of our universe captured in the faint, pervasive glow of the cosmic microwave background. It is a snapshot from when the cosmos was a mere 380,000 years old, a hot, dense and featureless fog of plasma. And when we look at this ancient light, we see something astonishing. It is almost perfectly smooth. The temperature variations, the seeds of all future structure, are minuscule, differing by only 1 part in 100,000. This profound smoothness presents a crippling paradox. The universe we inhabit today is the absolute antithesis of smooth. It is a tapestry of staggering complexity and contrast, a realm of brilliant condensed galaxies, separated by voids of unimaginable emptiness, a cosmic web of infinite intricacy. How could such a lumpy structured reality ever arise from such a bland and uniform beginning? The force responsible, we know, is gravity. Gravity acting over billions of years is the sculptor of the cosmos, pulling matter together, amplifying those tiny initial ripples. But there is a fatal flaw in this logic, a problem of time and strength. The gravity of ordinary matter alone, the protons, neutrons and electrons that constitute every star, planet and person, is remarkably feeble. In that early expanding universe, it was locked in a desperate battle. As gravity tried to pull atoms together, the outward pressure of intense radiation from the Big Bang relentlessly pushed them apart. The expansion of space itself was constantly working to dilute any nascent clump before it could gain a foothold. When we task our finest minds and most powerful computers with simulating this process, using only the laws of physics and the ordinary matter we can see, the result is always the same. The universe fails to be born. The simulation runs forward through billions of years of cosmic time, and the result is a desolate, almost featureless cosmos. A few small stunted dwarf galaxies might flicker into existence, but the grand spirals, the majestic ellipticals, the sprawling clusters, they are nowhere to be found. Our simulated universe remains a thin, homogeneous soup, a ghostly echo of its smooth beginning of failed creation. The luminous matter we are made of was simply too weak, too indecisive, too slow to overcome the universe's initial momentum. Our existence by this accounting should be impossible. This is where the story turns. This is where the ghost becomes the architect. To solve this impossible puzzle, cosmologists built new universes not with brick and mortar, but with trillions of lines of code. They created vast digital laboratories, the most ambitious of which was known as the Millennium Simulation. Inside this virtual cosmos, they could place billions of particles, dictate the fundamental laws of physics and press play, watching 13.8 billion years of cosmic evolution unfold in a matter of months. It was a tool of almost prophetic power, a way to test the very story of our origins. First they ran the simulation again with just ordinary baryonic matter, and again the result was a barren, empty expanse, a digital stillbirth. The universe we know and love refused to form. Then they introduced the ghost. They added a new type of particle to their digital creation, a particle that did not shine, did not reflect, did not absorb light. A particle that felt gravity and nothing else. They seeded their virtual cosmos with dark matter, 5 times more of it than all the visible matter combined, just as our observation suggested. And then, everything changed. The universe bloomed. What unfolded within the machine was a revelation, a glimpse into the silent, invisible processes that shaped our reality. Because dark matter does not interact with light or radiation, it was immune to the relentless pressure that held ordinary matter at bay. It had a head start. While photons blasted atoms apart, preventing them from clumping, the dark matter particles were free to answer gravity's call. Immediately after the Big Bang, in those same regions of infinitesimally higher density, seen in the cosmic microwave background, dark matter began to quietly and efficiently collapse upon itself. It was a silent, invisible construction project on a cosmic scale. Slowly, inexorably, these particles coalesced, forming vast spherical clouds of immense mass, the first dark matter halos. They were the primordial seeds, the invisible skeletons of the cosmos forged in the darkness of the early universe. They created what physicists call deep gravitational potential wells. Think of them as invisible valleys carved into the fabric of space-time. They were the cosmic scaffolding erected long before the first luminous bricks were ever laid. Without them, ordinary matter would have had nowhere to go, no anchor in the expanding cosmic sea. Now, with the stage set, the visible universe could finally make its entrance. The great clouds of hydrogen and helium gas, the stuff of future stars, found themselves adrift in a cosmos now dominated by these enormous invisible gravitational engines. The pull was irresistible. Drawn by this unseen summons, the gas began to fall, spiraling down into the centres of the dark matter, halos like water flowing into the deepest part of a basin. For the first time, ordinary matter had a gravitational focal point, powerful enough to overcome the outward forces pushing it apart. As the gas fell, it compressed. As it compressed, it heated up, a process of cosmic friction and collapse that concentrated matter to densities never before seen. And deep within the hearts of these ghostly cradles, a threshold was crossed. The pressure and temperature became so extreme that hydrogen atoms were forced together, their nuclei fusing in a flash of thermonuclear fire. The first stars ignited. It was a moment of cosmic dawn, the end of the Dark Ages, as billions of points of light blazed into existence across the universe, each one nestled safely within the gravitational embrace of a dark matter halo. This wasn't just the birth of stars, it was the birth of galaxies. Each halo acted as a celestial nursery, its immense gravity corralling the gas and stars, preventing them from flying apart. The spinning disk of the Milky Way, the brilliant bulge at its centre, the faint stellar halo that surrounds it. All of it is luminous paint applied to a vast invisible canvas. Our galaxy is merely the glowing visible tip of a colossal iceberg, a luminous jewel sitting at the gravitational heart of a dark matter halo 1,000,000 trillion times the mass of our Sun. Without that halo, the gas to form our star would have never collected. The Sun would have never lit. Our planet would never have formed. We are here because an invisible structure first prepared the way. The Millennium simulation revealed that this process was hierarchical. Small halos formed first, attracting enough gas to create the first small misshapen dwarf galaxies. But gravity is relentless. These smaller halos, each with their fledgling galaxies inside, were themselves drawn towards each other, pulled into the gravitational dominion of even larger, more massive dark matter halos that were forming. It was a cosmic food chain. Halos merged, colliding in slow, graceful ballets of gravitational chaos that spanned hundreds of millions of years. With each merger, the central galaxy grew larger, its gravitational pull stronger, its star formation more furious. Through this process of hierarchical assembly, the grand designs of the modern universe began to take shape. The collision and merger of smaller halos and their galaxies built the great spiral galaxies like our own Milky Way and Andromeda. Even more violent and numerous mergers in the densest regions of space forged the colossal elliptical galaxies, cosmic behemoths that sit at the hearts of galaxy clusters, their smooth rounded shapes the remnants of countless past galactic collisions. The simulation showed that the very morphology of a galaxy, its shape, its size, its type, is profoundly influenced by the merger history of the invisible halo in which it lives. The dark matter is the silent puppeteer, and the galaxies we see are the glowing puppets, their movements and final forms dictated by the unseen strings of gravity. But the simulation revealed a final, even more profound truth. The halos themselves were not distributed randomly. When the cosmologists zoomed out, viewing their entire digital universe at once, they saw that the dark matter had organized itself into a vast interconnected structure of breathtaking scale and complexity. It formed a cosmic web. Great long filaments of dark matter stretched across billions of light years, connecting massive dense nodes where halos clumped together. Between these filaments lay the great cosmic voids, immense deserts of emptiness largely devoid of both dark and luminous matter. It was the fundamental architecture of the universe, an invisible framework dictating where matter could and could not exist. And where the dark matter went, the visible matter had no choice but to follow. The galaxies, those brilliant points of light, were not scattered randomly either. They were strung along the filaments of the cosmic web like pearls on a string. They populated the great nodes forming the superclusters of galaxies that are the largest gravitationally bound structures we know. The simulation had not just created individual galaxies, it had created the entire large-scale structure of the cosmos. The most breathtaking moment came when the scientists compared the final state of their simulation, this intricate web-like pattern, to the real maps of the universe created by our Deep Sky Telescope surveys. The resemblance was uncanny. The digital universe born from the laws of physics and the inclusion of dark matter looked exactly like the real one. The number of clusters, the spacing of the voids, the filamentary structure, it all matched with stunning precision. This was the ultimate confirmation. Dark matter was not just some fudge factor needed to explain spinning galaxies. It was the master architect. It was the primordial seed. It was the invisible scaffolding upon which every star, every galaxy, and every cluster was painstakingly assembled. It built the cosmic web, the very bones of the universe, and then guided the luminous matter to flow into place, decorating its grand design with light and life. The problem of its existence was dwarfed by the revelation of its purpose. We don't live in a universe that simply contains dark matter. We live in a universe that exists because of it. The implications are almost philosophical in their depth. Everything we see when we look out into the night sky, every nebula, every star, every distant galaxy, is just the brilliant ephemeral foam on a deep invisible ocean. We have spent centuries mapping the locations of the lights, believing we were mapping the universe. But we were only ever mapping the highlights, the glowing embroidery on a vast dark tapestry that constitutes the true substance of reality. The real structure, the underlying truth, remains unseen. We have unmasked the architect, we have seen its grand blueprint, and we have witnessed its construction in our virtual worlds. We have shifted our understanding of dark matter from a mere problem to be solved to the fundamental solution for our own existence. Yet this profound revelation only serves to sharpen the central mystery, to bring the most vital question into stark, unavoidable focus. If this invisible substance is the cosmic bedrock, the foundation of all things, the glue that binds the cosmos and the cradle in which we were born, then what in heaven's name is it? What is the nature of this ghostly particle that so profoundly, yet so silently governs the fate of everything we will ever know? And so with the cosmic web unfurled across our supercomputers, a grand digital tapestry woven from the laws of physics, and a single vital ingredient, cold dark matter, we had seemingly cracked the code of creation. The lambda CDM model was more than a theory. It was a stunning artistic and scientific triumph. It gave us the great filaments of galaxies, the vast voids, the colossal clusters standing like celestial cities at the intersections, all recreated with breathtaking fidelity. On the largest of scales, our simulations were not just good, they were uncannily prophetically correct. We had built a universe in a box that looked for all the world like the one we saw through our telescopes. It was a moment of profound clarity, a peak of understanding from which we could look down upon the whole of cosmic history. But science is a restless endeavour. Its gaze is never fixed on the summit for long. The true test of any grand theory lies not just in its panoramic vistas, but in its fine, granular details. And so we began the downward path, a journey of scale zooming in from the cosmic web that spans billions of light years to the intimate confines of our own galactic neighbourhood. We pointed our virtual telescopes not at the great clusters, but at the simulated halos meant to represent our very own Milky Way. And here in our own backyard, in the quiet darkness between the stars, the beautiful symphony of lambda CDM began to falter. The pristine mathematical edifice started to show cracks, not large catastrophic failures, but small insidious and deeply troubling inconsistencies. The grand truth of the universe, it seemed, was being challenged by a series of whispers from the dark. The first of these disquieting whispers grew into a roar, a problem of presence, or rather profound absence. Our models, those same triumphant simulations, were unequivocal. A massive dark matter halo like the one cradling our Milky Way should not be a solitary monolithic object. It should be a fractal of itself, a great gravitational monarch surrounded by an immense and loyal court. The theory predicted that our galaxy should be swarming, absolutely infested with thousands upon thousands of smaller subhalos of dark matter, gravitational satellites orbiting the primary mass. Each of these subhalos, a cosmic seed in its own right, should have been massive enough to capture interstellar gas to ignite the fires of starbirth, and to blossom into a dwarf galaxy, a small luminous companion tethered to us by gravity. The predictions painted a glorious picture. The night sky seen from some distant vantage point should show the Milky Way attended by a glittering cloud of satellites, a celestial queen with a retinue of star-flecked handmaidens. So we looked. With ever more powerful telescopes, we began a cosmic census, scanning the void around us for these predicted companions. We found the Magellanic Clouds brilliant and obvious. We found Sagittarius Fornax Leo 1 Sculptor. Slowly, painstakingly, over decades of searching the Sloan Digital Sky Survey. And others began to uncover fainter, more ephemeral ghosts. Tiny, ultra-faint dwarf galaxies, some with only a few thousand stars barely holding on. The count grew from a dozen to 2 dozen, then 3, then 4. But as our technology improved and our surveys deepened, a chilling realization began to dawn. The numbers were not adding up. Not by a little. Not by a factor of 2 or even 10. Our simulations were screaming that there should be thousands. Our telescopes were whispering back, a few dozen. This was the missing satellites problem. It was as if we had predicted a thriving, bustling metropolis and arrived to find a quiet, sparsely populated town. Where was everybody? Where were the missing children of the Milky Way? The discrepancy was so vast, so staggeringly huge, that it struck at the very heart of the theory. It was the first profound challenge from the small scales. Perhaps some argued these subhalos were simply dark. Maybe they existed as predicted pure globes of dark matter, but for some reason failed to capture gas and ignite stars. They could be a population of invisible failures, ghost galaxies haunting the edge of our own. This was a comforting thought, a way to save the model. It shifted the blame from the physics of dark matter to the messy, complicated physics of star formation. But even this explanation felt incomplete, an answer that raised more questions than it solved. Why would so many, the vast majority, fail so completely? What cosmic blight had sterilized these thousands of galactic seeds? Or was the truth more fundamental? Perhaps the subhalos, the seeds themselves, were never there at all. Perhaps the model was simply wrong, overproducing these small structures in its digital universe, creating a phantom population that had no counterpart in reality. The silent, empty court of the Milky Way stood as a stark rebuke, a cosmic mystery that cast a long shadow over the celebrated success of cold, dark matter. But the puzzles were only just beginning. The mystery of the missing satellites was one of quantity. The next anomaly we discovered was one of quality of character, of the very shape of the darkness itself. It forced us to peer not just around our galaxy, but deep within it, and into the hearts of the few dwarf companions we could find. The question was simple. What is the structure of a dark matter halo? What does its density profile actually look like? Again, the Lambda CDM model made an incredibly specific, unambiguous prediction, a consequence of dark matter's cold nature. Being cold simply means the particles were moving slowly in the early universe, allowing gravity to pull them together effortlessly and efficiently from the very beginning. As these halos collapsed and grew over billions of years, the particles interacting only through gravity would fall toward the center, creating a dense, compact core. The simulations were resolute on this point. Every time we ran the numbers, the result was the same. The density of dark matter should not be uniform. It should rise steadily from the outskirts of the halo inward, and then in the very center, it should spike dramatically, forming what astronomers call a cusp. Imagine a mountain peak. A cusp is a sharp, jagged summit, a gravitational spire rising to an almost infinite density. A core, by contrast, is a flattened plateau, a mountain with its top sheared off, creating a broad, less dense central region. The cold dark matter model predicted a universe full of cusps. Every galaxy, from the largest spiral to the smallest dwarf, should be impaled upon one of these sharp gravitational spikes. This was a testable prediction. We couldn't see the dark matter directly, but we could map its influence with exquisite precision. By tracking the orbits of stars and clouds of hydrogen gas, we can effectively weigh a galaxy, measuring how much mass is contained within any given radius. If a galaxy has a dense cuspy, dark matter halo stars and gas near the galactic centre, should be caught in a fierce gravitational grip whipping around at tremendous speeds. If, however, it has a cored halo, the gravitational pull at the centre will be weaker, and the orbital velocities will be correspondingly slower. So we turned our instruments to the nearby dwarf galaxies, the very survivors of the missing satellites problem. These small, faint galaxies are perfect laboratories for this test. They are utterly dominated by dark matter. The gravitational influence of their few stars is almost negligible. What we measured there was the true unadulterated shape of the underlying invisible halo. And what we found again and again was a direct and stunning contradiction. The stars were moving too slowly. Their lazy, gentle orbits bespoke a gravitational field that was far weaker at the centre than the models foretold. Instead of a sharp, menacing cusp, we found a soft, gentle core. The gravitational mountain had a flattened top. The spear point was blunted. This became known as the core cusp problem, and it was in many ways even more profound than the first. It wasn't just about the number of halos, but their very nature. It suggested that the fundamental physics baked into our simulations, the idea of dark matter as a simple, cold, collisionless particle, might be fundamentally flawed. Something was happening in the real universe that our models were blind to. Something was smoothing out these central cusps, some physical process that could actively push dark matter away from the galactic centre, or perhaps prevent it from accumulating there in the first place. Could it be the explosive feedback from supernovae? Perhaps waves of baryonic matter blasted outward by dying stars could stir up the dark matter, softening its central density. This was a plausible idea, an attempt once more to blame the complex physics of normal matter for the model's shortcomings. Yet for the smallest dwarf galaxies where this discrepancy was most glaring, it was unclear if they had enough star formation, enough firepower, to perform such a dramatic act of gravitational engineering. The core cusp problem hung in the air, a deep structural flaw in our understanding. We were missing the satellites, and the few we could find were built all wrong. The elegant theory was beginning to look decidedly frayed at the edges, but there was a third challenge, a final twist of the knife that was in some ways the most subtle and damning of all. It combined the issues of population and structure into one, creating a paradox that became known by a wonderfully confident, almost arrogant name, the too big to fail problem. The Lambda CDM simulations didn't just predict a certain number of subhalos, they predicted their mass distribution. Most would be small, but the model guaranteed the existence of a select few, a dozen or so of truly massive subhalos, orbiting a host like the Milky Way. These weren't the lightweight seeds that might struggle to form a galaxy. These were the cosmic titans, the gravitational royalty of the subhalo court. Their gravitational wells were predicted to be so deep, so powerful, that they should have been inescapable traps for gas in the early universe. According to every law of physics, we understood it should have been impossible for them not to form large, brilliant and easily detectable satellite galaxies. They were quite literally too big to fail, so the search was on. We knew what we were looking for. The simulations told us precisely the masses of these top-tier subhalos. All we had to do was look at our own sky, identify the brightest, most massive satellite galaxies orbiting the Milky Way, and see if they matched. We looked at the large and small Magellanic Clouds, our most prominent companions. We looked at the Sagittarius dwarf currently being torn apart by our galaxy's tides. We carefully measured their total mass, not just their stars, but their dark matter halos, by analysing the motions of their stellar populations and globular clusters. And when the calculations were done, a new paradox emerged, more perplexing than the others. The actual observed satellite galaxies of the Milky Way, our brightest and best, were all significantly less massive, less dense than the dozen most massive subhalos predicted by the simulations. This was a profound disconnect. It was as if we had a list of the 10 wealthiest people who were supposed to be living in a city, and when we went to their mansions we found them occupied by people with far less wealth, while the true billionaires were nowhere to be found. Where were the real gravitational behemoths that the simulations demanded? The model was unequivocal: they must exist. They are the most massive, most tightly bound structures that should have survived the galaxy formation process intact. Yet they do not seem to host the luminous galaxies we see. This problem couldn't be easily dismissed by invoking inefficient star formation. These subhalos were so colossal that their gravity should have overwhelmed any stellar feedback. It left us with two deeply uncomfortable possibilities. Possibility 1, the universe's most massive subhalos are for some completely unknown reason entirely dark. They are ghostly leviathans, invisible titans orbiting us right now, each more massive than any satellite galaxy we can see, but utterly devoid of stars, gas, or light. They are the true kings who never claimed their thrones. Possibility 2, they simply do not exist. The simulations are fundamentally wrong about the properties of the most massive subhalos, creating phantom giants that have no basis in reality, a missing census, the wrong internal architecture, and a court of luminous princes where there should be kings. These were not small academic quibbles. Taken together, the missing satellites, the Caucus problem, and the too big to fail paradox formed a powerful trifecta of evidence, a chorus of dissent rising from the small-scale universe. They told us that for all its grandeur and success on cosmic scales, our beautiful model was deeply, fundamentally incomplete. It was like a magnificent clock that perfectly tracked the turning of the years and the seasons, but could not account for the ticking of the seconds. For decades, these problems have resisted every easy solution, pushing astronomers and physicists to the very edge of their imagination. They force us to confront the most basic questions we thought we had answered. Is the darkness itself more complex than we ever conceived? Is dark matter not the simple inert particle of our theories? Could it feel a force other than gravity, a form of self-interaction that allows it to spread out, softening its own cusps? Does it have a faint warmth, a residual velocity that prevents it from clumping so readily on the smallest scales, thereby preventing the formation of countless dwarf galaxies? Or perhaps have we been looking in the wrong place all along? Maybe the fault lies not in the dark but in the light. Perhaps the physics of the stars, the chaotic, violent and explosive processes of baryonic matter are far more powerful and influential than we ever gave them credit for. Could the cumulative blast from billions of supernovae over cosmic time be enough to fundamentally re-engineer the gravitational landscape of a galaxy, expelling dark matter from the centre and solving all three problems at once? The path forward splits into two tantalizing directions. One leads us inward to the subatomic realm, forcing us to rethink the very identity of the particle that holds our universe together. The other leads us outward into the fiery hearts of galaxies, demanding a new appreciation for the cosmic battle between gravity and light. The simple, elegant picture of cold, dark matter has been challenged. And from the heart of that challenge, a new and more intricate cosmology is struggling to be born, one that promises a universe even stranger and more magnificent than our most daring theories. The evidence now is overwhelming. We have traced the grand gravitational architecture of the cosmos and found that its most fundamental blueprints are written in an invisible ink. We have watched galaxies spin with impossible speed, held together by an unseen shepherd. We have seen light bend around nothingness, revealing the contours of a hidden ocean of mass. The dark matter halo is no longer a fringe theory. It is a central pillar of our cosmic understanding, a ghost whose presence is felt everywhere. But feeling a ghost is not enough. Science demands an encounter. The time for mapping shadows has passed. Now we must turn on the lights. Now the hunt begins. This is the story of that hunt. It is a quest that pushes human ingenuity to its absolute limits, a search for a particle so reclusive it makes the neutrino look like a socialite. This is not a search conducted with a single telescope or a lone brilliant mind. It is a global, multi-generational assault on the unknown, a three-front war waged against the darkness. We are fighting on the ground, in the heavens, and in the very heart of recreated Big Bangs. Each front represents a unique strategy, a different way to corner a quarry that has for nearly a century refused to be seen. If the dark matter particle exists, it cannot hide from this cosmic dragnet forever. One of these methods we believe must succeed. The fate of cosmology hangs in the balance. Our first battlefield is perhaps the most unlikely deep beneath your feet. To find the quietest particle in the universe, we have to travel to the quietest places on Earth. We must descend through kilometers of solid rock, journeying into the subterranean dark to escape the ceaseless storm of cosmic radiation that constantly bombards our planet's surface. This cosmic static, a shower of particles from the sun and distant supernova, would utterly drown out the whisper-faint signal we're hoping to hear. The rock of the Earth itself becomes our shield, a planetary filter against the noise of the universe. Down here in the profound geological silence, we build our traps. Welcome to the Sanford Underground Research Facility in South Dakota, or the Gran Sasso National Laboratory in Italy. Here in vast caverns carved from ancient stone sit some of the most sensitive machines ever conceived by humanity. They are experiments like the Lux Zeppelin or LZ detector, and its counterpart in Europe, Xenont. They are not telescopes looking out, but technological shrines waiting for something to wander in. The principle behind them is one of elegant simplicity masking an almost absurd technical challenge. We know the Earth in its orbit around the Milky Way is constantly ploughing through the galaxy's enormous dark matter halo. We are flying through a thick invisible wind of these particles at hundreds of kilometers per second. If we can build a detector pure enough and sensitive enough, just maybe one of those billions of particles passing through you every second will by sheer chance strike one of our carefully prepared atomic nuclei. It is a search for the gentlest of cosmic nudges. The detector itself is a colossal vat, a time projection chamber filled with multiple tons of hyper-purified liquid xenon. We choose xenon because its atoms are enormous, presenting a large target for a potential collision. The liquid is kept cryogenically cold, purer than anything found in nature, scrubbed of almost every last radioactive atom that could create a false signal. This vast, silent volume of liquid is surrounded by hundreds of photomultiplier tubes instruments, so sensitive they can register the arrival of a single photon of light. They are the electronic eyes of the experiment waiting in the absolute dark. The entire apparatus is then submerged in an even larger tank of purified water, a final layer of shielding to catch any stray neutrons from the surrounding rock. Here is what we are waiting for, the signal that would change the world. A WIMP, a weakly, interacting massive particle. Our leading candidate for dark matter drifts invisibly into the heart of the detector. Against all odds, it strikes a xenon nucleus not with the force of a cosmic ray, but with the delicate touch of a phantom. The recoiling nucleus excites the surrounding xenon atoms, producing an immediate tiny flash of ultraviolet light. This is the first signal, the S1 pulse. The collision also knocks a few electrons free from the xenon atom. A powerful electric field, carefully maintained across the chamber, gently pulls these orphaned electrons upwards, causing them to drift through the liquid. When they reach the top, they are accelerated into a layer of xenon gas, creating a second brighter flash of light, the S2 pulse. The beauty of this two-signal system is its power of rejection. The timing between the first and second flash tells us the precise depth of the interaction. The pattern of the light allows us to reconstruct its 3D position within the detector. Crucially, the ratio of the two signals, light versus charge, is different for a WIMP-like collision compared to a collision with a stray electron or gamma ray. This gives us an almost magical ability to distinguish our sought-after signal from the background noise. It is a gravitational ghost detector designed to see one specific kind of phantom and ignore all others. For years, these experiments have sat in the dark listening. They are monuments to patience, a symphony of silence where the crescendo is a single fleeting interaction. So far, the silence has been deafening. But with each passing day of quiet, we are not failing. We are methodically, relentlessly tightening the noose, eliminating possibilities, and forcing the true nature of dark matter out of the shadows. While one army waits in ambush, another has decided to forge the enemy from scratch. If dark matter will not come to us, we will create it ourselves. This second front in our war is not in the quiet depths, but in a place of unimaginable violence and energy, the Large Hadron Collider at CERN. The LHC is a 27-kilometer ring of superconducting magnets, a subterranean racetrack designed to accelerate protons to 9010 neos, 1% of the speed of light. Here we do not shield ourselves from energy. We generate it. We create conditions that have not existed in the universe since the first trillionth of a second after the Big Bang. Two beams of protons, each carrying the kinetic energy of a freight train, are smashed together inside cathedral-sized detectors. In these miniature fireballs of creation, matter and energy blur, governed by Einstein's famous equation E=mc2. From the pure energy of the collision, a zoo of exotic fundamental particles flashes into existence. Our hope is that among the quarks, bosons and muons that fly from the impact point, we might also produce a pair of dark matter particles. This strategy, however, comes with a profound paradox. How do you detect a particle whose defining characteristic is that it doesn't interact with your detector? The answer is as clever as it is counterintuitive. We don't look for the particle itself. We look for its absence. We hunt for the energy it steals. The detectors at the LHC, like Atlas and CMS, are technological marvels layered like gargantuan onions to track every known particle that emerges from a collision. They measure the trajectory, momentum, and energy of every quark, every lepton, every photon with breathtaking precision. According to the fundamental laws of physics, the momentum of all the debris flying out from the collision must be perfectly balanced. It's a law of cosmic accounting. Imagine a silent explosion in deep space. If you see all the shrapnel flying out to one side, you know with absolute certainty that something unseen must have flown out in the opposite direction to balance the event. This is precisely what physicists at the LHC are searching for. They meticulously sum up the energy and momentum of every single particle they can see. If the final sum doesn't add up to zero, if there is a significant amount of missing transverse energy, as they call it, all pointing in one direction, it is a colossal clue. That missing energy could be the signature of a dark matter particle or two having been produced in the collision and then passing straight through the multi-thousand-ton detector as if it were empty space, leaving behind only a hole in the ledger. It is the ultimate particle physics magic trick. We see the puff of smoke, and from it we infer the magician who has vanished. The collider gives us a power the underground experiments lack. If we succeed in producing dark matter, we will not just know it exists, we will learn its properties. The specific amount of missing energy could tell us its mass. The other particles produced alongside it in the collision, the so-called signature, could reveal how it connects to the particles we know and love. It would be like finding a fossilized key that unlocks the door to a whole new dark sector of physics, a parallel family of particles and forces that mirrors our own. This alchemical forge-smashing matter to recreate the dawn of time could provide the direct detection experiments with a treasure map telling them exactly what mass to look for, what kind of ping to expect. The two fronts are not in competition. They are in a deep symbiotic partnership, one creating the blueprint, the other searching for the finished product out in the wild. But even this two-pronged attack is not enough. The universe is vast and our quarry is cunning, and so we have opened a third front. This final strategy takes us away from the Earth out into the cosmos itself. We turn our gaze toward the heavens not to search for a single particle, but to listen for the faint collective echo of its existence. This is the path of indirect detection, and it is a hunt for a celestial crime scene. The theory is straightforward. While a single dark matter particle is incredibly unlikely to interact with normal matter, the dark matter halos themselves are incomprehensibly dense, especially towards the centers of galaxies. In these gravitational wells where trillions upon trillions of dark matter particles are churned together, they should occasionally collide with each other. If our leading theories are correct, when two dark matter particles meet, they can annihilate. They vanish in a burst of energy, a burst that decays into a shower of familiar high-energy particles, gamma rays, positrons, and antiprotons. These annihilation products are our signal. They are the cosmic breadcrumbs that could lead us back to the source. We cannot see the dark matter, but we might be able to see the faint glow of its self-destruction. To do this, we have deployed advanced observatories in orbit, placing them above the distorting veil of the Earth's atmosphere. The Fermi Gamma Ray Space Telescope tirelessly scans the entire sky, mapping the universe in the most energetic form of light. It is searching for an excess of gamma rays coming from places where we expect dark matter to be thickest, the dense churning heart of our own Milky Way, or the small, faint dwarf satellite galaxies that orbit us, which are known to be almost entirely composed of dark matter. A mysterious, inexplicable glow of gamma rays from one of these locations would be a smoking gun. And tantalizingly, Fermi has seen something. For years, scientists have analysed a strange spherical haze of excess gamma rays emanating from the galactic centre, an energy signature that doesn't quite match our models of known astrophysical sources like pulsars or black holes. This galactic centre excess fits the profile of certain dark matter annihilation models almost perfectly. It could be the signal we have all been waiting for the first glimpse of the dark sector in action. Or it could be a collection of thousands of undiscovered faint pulsars, a new astronomical phenomenon masquerading as our prize. The debate rages on a perfect example of the scientific process in motion, where extraordinary claims require truly extraordinary evidence. Attached to the International Space Station, another revolutionary experiment joins the hunt. The Alpha Magnetic Spectrometer, AMSC02, is not a telescope. It is a particle detector in space. As cosmic rays, high-energy particles from deep space rain down on it, its powerful magnet bends their paths, allowing it to distinguish matter from antimatter with exquisite precision. One of its primary missions is to search for an excess of positrons, the antimatter equivalent of electrons. Dark matter annihilation is one of the few exotic sources predicted to produce a large number of these particles at very specific energies. And just like Fermi, AMS-02 has also found a mystery. It has detected significantly more high-energy positrons than expected from known cosmic sources. The signal is clear, but its origin remains shrouded in ambiguity. Nearby pulsars are again a leading conventional explanation, but the possibility that we are seeing the decay products of dark matter remains thrillingly on the table. Here then our climactic search stands today, a trinity of strategies each pushing the boundaries of technology and human perseverance. We are waiting in the silent dark deep underground for a single ghostly knock upon a single atom. We are smashing matter with godlike power in our colliders, searching for a telltale absence in the resulting storm of creation. And we are looking out into the void, scanning the heavens for the faint ghostly embers of annihilation from the heart of the halo itself. It is a siege laid from every possible direction. The web is woven, the traps are set. Every year the detectors become more sensitive, the colliders more powerful, the telescopes more precise. With every null result, we learn more, refining our theories and closing off the hiding places for this elusive particle. Discovering its nature would be more than just solving the mystery of the galactic halos. It would be a moment of transformation for our species, a revelation on par with the discovery of the atom or the confirmation of the Big Bang. It would prove that the universe we see, the stars, the galaxies, the planets and ourselves, is merely the foam on the surface of a much deeper, darker and stranger cosmic ocean. We would finally have the key to understanding the invisible 95% of reality. The stakes could not be higher. We have asked the universe its most profound question, and now across our planet and beyond in the silent depths, and the violent forges and the patient eyes of our satellites, we hold our breath and we listen for the answer. And so, after a long journey through the cosmic dark, we arrive here. We have stood on the shoulders of giants, from the cantankerous Fritz Zwicky, who first heard the discordant whispers of missing mass in the Coma Cluster, to the quiet, unwavering resolve of Vera Rubin, who listened to the songs of spinning galaxies and found a note that simply should not have been there. We have followed a trail of clues that began not as a clear signpost, but as a subtle, persistent anomaly, a stubborn refusal by the universe to obey the laws of physics as we had written them. It was a cosmic error message flashing in the peripheral vision of astronomy for decades, an error that pointed not to a flaw in our calculations, but to a breathtaking omission in our understanding of reality itself. We have seen how that initial puzzle, the impossibly fast spin of stars at a galaxy's edge, became the first thread in a vast invisible tapestry. Pulling on it revealed a universe far stranger and more magnificent than we had ever conceived. We learned that the brilliant, shimmering spiral of a galaxy like our own is not an island of matter in an empty void. Instead, it is merely the glowing froth on the shore of an immense unseen ocean. we came to understand that every star, every nebula, every planet we have ever charted is embedded within a colossal spherical halo of a substance that emits no light, reflects no radiation, and feels none of the forces that govern our everyday existence save for one gravity. This is the profound revelation of the dark matter halo. It is not merely a component of the universe, it is the universe's primary architecture, its foundational bedrock. To grasp this truth, we had to learn a new way of seeing. We turned our telescopes to the heavens and witnessed gravity itself performing a celestial magic trick. We watched the light from distant quasars bend and distort as it passed by intervening galaxies, creating ghostly arcs and eerie multiple images of the same object. This gravitational lensing was the universe's own way of weighing itself, and the scales tipped dramatically. The warping of space-time was far too extreme to be caused by the visible matter alone. It was the unmistakable signature of a colossal invisible mass, the dark halo itself acting as a cosmic lens, its presence betrayed only by the path of light it commandeered. We had found a way to photograph a ghost not with a camera, but with the very fabric of space-time. The evidence continued to accumulate, each piece a new verse in this epic of the unseen. We looked back in time all the way to the dawn of creation, examining the faint fossilized afterglow of the Big Bang, the cosmic microwave background. There imprinted on this baby picture of the universe were the subtle temperature variations, the primordial seeds from which all cosmic structure would eventually grow. Our most sophisticated simulations confirmed a stark reality. A universe made only of ordinary matter could never have produced these patterns. The gentle gravitational pull of atoms alone was too feeble, too slow to gather matter into the vast clusters and filaments we see today. The simulations only worked, only produced a cosmos that looked like our own, when we introduced a vast, cold, non-interactive substance. Dark matter. It was the silent shepherd of the early universe, its immense gravity creating the cosmic wells, the gravitational wombs into which ordinary matter could fall cool and ignite into the first stars and galaxies. Without the pre-existing scaffold of dark matter halos, we simply would not be here. The Milky Way would not exist. The sun would never have formed. Our existence is predicated on a substance we cannot touch, see, or comprehend. And so we find ourselves in the present moment standing at the precipice of a new frontier. The hunt is on, and it is one of the most ambitious and daring scientific quests ever undertaken by humankind. It is a search being conducted not just with telescopes that look out, but with detectors of almost spiritual purity that look inward, buried deep within the Earth's crust. In former gold mines and beneath sacred mountains shielded by miles of solid rock, from the confusing chatter of cosmic rays, physicists wait in profound silence. They wait for a single fleeting interaction. A WIMP, a weakly interacting massive particle. One of the leading candidates for dark matter might just once in a decade strike an atom in a vat of supercooled liquid xenon or a crystal of germanium with impossible clarity. The collision would be unimaginably gentle, a phantom knock on the door of our reality releasing a tiny flash of light or a subtle vibration, a signal so faint it pushes the very limits of our technological senses. These subterranean laboratories are modern-day cathedrals of science built to listen for a whisper from the dark universe that flows through us and around us at every moment. For we are right now moving through our own galaxy's dark matter halo at hundreds of kilometers per second. Trillions of these mysterious particles are likely streaming through your body as you watch this passing through the screen, through the Earth itself, as if none of it were there. To detect just one of these cosmic ghosts is the goal. To capture one is to finally grasp the invisible substance that holds our galactic home together. It would be a discovery that would not just earn a Nobel Prize, but would redefine the very periodic table of the universe, adding a new element not of matter as we know it, but of something entirely different. Yet the Deep Earth experiments are not our only hope. Elsewhere, scientists are searching for a different kind of phantom, the axion. This contender is incomprehensibly lightweight, and if it exists, would behave more like a pervasive oscillating field than a particle. In chambers filled with some of the most powerful magnetic fields ever generated by humanity, researchers are trying to coax these axions to convert into a single detectable photon. It is an experiment of exquisite subtlety, like trying to hear a single pure note in a symphony of cosmic static. The successful detection of an axion would be just as revolutionary, proving that the dark universe might be even more ethereal and strange than we imagined. And above us in orbit, powerful telescopes like the Fermi and the AMS are searching for telltale signs of dark matter particles annihilating each other in the dense heart of the Milky Way, a potential burst of gamma rays or antimatter that would be the dying scream of these elusive entities. This global multi-generational hunt from the deepest mines to the highest orbits underscores the sheer magnitude of the mystery. What if dark matter is not one thing but many? We speak of dark matter as if it were a single monolithic substance. But what if that is as naive as an ancient philosopher believing all celestial bodies were made of a single, fifth element? Perhaps we are on the verge of discovering not just a new particle, but an entire dark sector of the universe, with its own family of particles, its own complex forces, a shadow, physics that mirrors our own in its complexity, but remains almost entirely deaf to our world. Could there be dark atoms, dark chemistry, perhaps even dark light, all interacting in a parallel cosmos that coexists with ours, bound to us only by the universal reach of gravity? The possibilities are as tantalizing as they are humbling, reminding us that our familiar world of light and matter might be just one facet of a far richer, more complex reality. Finding the particle or particles of dark matter will be more than just filling a blank in our cosmological models. It will be akin to discovering a new fundamental force of nature, a new set of rules for how the universe works. The properties of this particle, its mass, its interactions, its history, hold the keys to answering some of the most profound questions we can ask. By understanding dark matter, we will finally understand the complete story of galactic evolution. We will be able to trace the cosmic web from its primordial roots, watching how these halos grew, how they merged in titanic slow-motion collisions over billions of years, and how these gravitational dances sculpted the galaxies we see today. We will understand why some galaxies are majestic spirals while others are disordered elliptical giants. The invisible halo is the puppet master, and by seeing it, we will finally see the strings. But the implications stretch far beyond the fate of individual galaxies. The total amount of dark matter in the universe and its fundamental nature will help determine the ultimate destiny of everything. Is there enough of this unseen mass to eventually halt the expansion of the universe, to pull everything back together in an ultimate big crunch? Or is its gravitational influence, though vast, still insufficient to overcome the mysterious outward push of dark energy, leaving the cosmos to expand forever into a cold, dark and lonely eternity known as the Big Freeze? The answer lies encoded in the identity of the very substance that forms the halos around us. These invisible structures are not just the anchors of the present, they are the gyroscopes of cosmic destiny, their collective gravity steering the entire universe toward its final inescapable fate. So we conclude our journey where we began, in awe of the unseen. We have traversed the history of an idea from a flicker of doubt in the mind of an astronomer to the central pillar of modern cosmology. We have learned that the universe we see is but a luminous minority, a dusting of cosmic glitter on a vast dark canvas. The discovery of dark matter halos represents a profound shift in human perspective, as significant as the Copernican revolution that displaced the Earth from the centre of the universe. We now know that not even the matter we are made of is central. We are the anomaly, the rare exception in a cosmos dominated by a substance that is fundamentally alien to our experience. The path forward is uncertain, paved with both the promise of imminent discovery and the daunting possibility of ever deeper mystery. But the quest itself is a testament to the relentless curiosity that defines our species. It is the drive to look into the darkness and not be afraid, but to be inspired. It is the refusal to accept that what we see is all there is. For centuries we have looked up at the pinwheels of distant galaxies, admiring their beauty, their light, their structure. Now we understand that their true majesty, their true nature lies in the immense invisible architecture that gives them form and life. The greatest structures in the universe are the ones we cannot see, the silent gravitational ghosts that have shaped the cosmos from the very beginning. and in our search for them we're doing more than solving a cosmic puzzle. We are holding up a mirror to our own ignorance, and in doing so preparing ourselves for a revelation that will forever change our place in the cosmos. The dark matter halo is the ultimate reminder that the most profound truths are often hidden, waiting patiently in the dark for us to invent new ways to see.